Wait, okay. As you may know, I'm a sophomore and I like doing math and computer science competitions. Today, I'll be talking about basic functional equations and how to solve them. What is a functional equation? Well, a functional equation is an equation which asks you to find all functions which satisfy certain requirements. Generally, they don't appear that much on AMY or AMC, but it does appear occasionally. But these are mostly Olympiad level concepts and can help you get easy points on the USHMO or USAMO. For example, a functional equation would be something like the example I have on the slide. So f of x plus y equals to f of x plus f of y. And what the problem is asking you to do is, given a domain and a range, you want to find all functions that satisfy that requirement. And not only do you have to prove that they're the only functions that satisfy the requirement, you also have to prove that all of the functions satisfy the requirement. So after you prove that the only functions that are possible are a certain list of functions, you have to actually plug those functions back into the equation as your last step to verify that they actually work. The easiest functional equations are the ones where all you need to do is plug in numbers. Generally, the first thing you should do when solving functional equations is to just plug in a bunch of convenient numbers for x and y. So for example, if you plug in x equals 0 and y equals 0, generally you'll be able to find an expression for f of 0, or you would be able to find something else. That would be very, very convenient. So in my example problem, you have f from domain of reals to a range of reals, so from reals to reals, such that f of x plus y squared all squared equals to 2 f of x plus 5y minus 1. Yeah, I'll give you a couple minutes to think about this problem. Just keep in mind that you want to plug in convenient numbers which cancel a lot of terms, and you also um, want to find convenient values of f of x. So for example, if you want to find f of 0, you want to figure out a way to do that. I'll give you a couple minutes to think about this problem and if there's a solution to this problem that you can figure out. Also, feel free to just like, if you have an idea, send a chat message to me or send like, or maybe like say it out loud if you want. But if you're shy, you can just send a chat message to me. Okay, so if there are no solutions, then I guess I'll talk about the insight into how to solve this problem. So this problem, essentially, you want to try to plug in as many numbers as you can and figure out what the most promising line of thought is. So the first thing you do is you plug in 0 and 0, and you get that f of 0 squared. You get that f of 0 squared equals to 2 f of 0 minus 1. So you get f of 0 squared equals 2 f of 0 minus 1. And from this equation, you can easily see that f of 0 equals 1. So now you're thinking like, okay, what if we want to expand this. So what if we plug in like y equals something? Well, the 5 seems rather arbitrary. So what if we plug in y equals 0? Well, if we plug in y equals 0, we just get the f of x squared, right, equals 2f of x minus 1. And this similarly shows you that f of x equals to 1. Okay, now we just plug in f of x equals 1 back into the original equation, and we get that 1 squared equals to 2 times 1 minus 1, which is clearly true. Um, so, yeah, here we have that if we plug in y equals 0, so this is like the formal proof. So if we plug in y equals 0, then we have f of x squared equals to 2f of x minus 1. So f of x equals 1, and we get that. It's true, so yeah. Another technique when trying to plug in like random values is that maybe if convenient values don't work, then you might want to plug in an expression that can cancel out other terms. So for example, if one of the terms is very, very ugly and you don't want to deal with it, you can try to plug in y in terms of x to try to cancel that term out with something else. And if you are able to do that, you would be left with a much, much simpler functional equation, and you could potentially be able to solve that easily. So here's the example problem. So again, f goes from the reals to the reals, and f of 3x to the 6 minus 8y squared equals f of 5y minus 4 over 2 x to the 264 plus f of x to the 7. Um, oh, wait, okay. Again, I'll give you 2 minutes to think about this problem and how you would be able to cancel things out. Again, if you think you have a solution, you can send a message to me or just like say your answer out loud. Well, again, if there are no solutions to this problem, um, we can talk about the solution. So the solution revolves around canceling the first term over here and the first term on the right. So in order to cancel the first term with the first term on the right, we want to set them equal to each other. So that's why we're trying to set them equal to each other and solve for y. And in this case, we get a really, really complicated expression. But the important part is that y is defined. And how do we know y is defined? Well, we know that 3x to the 6 over 8 is positive. We know that 1 over 2x to the 264 is also positive. And we know that 25 over 256 is also positive. So the entire thing under the radical is positive, which means that the square root is defined. And so for every x other than 0, there would be a y which is defined, which cancels the first two terms. And this is super important because once we cancel those first two terms, all we get left is that f of x to the 7 equals to 0. And the range of x to the 7 is all reals. So all non-zero reals satisfy that f of x equals 0. And to prove that f of 0 equals to 0, we just need to set that 3x to the 6 equals to 8y squared. And since the other two terms, since the two terms on the right-hand side are both 0, that means that f of 0 equals to 0. So f of x equals 0. And when we plug it back into the original equation over here, we get that 0 equals 0 plus 0, which is clearly true. However, plugging things in and trying to cancel terms isn't going to solve every single functional equation. That's why we need injectivity, bijectivity, and surjectivity. If we prove one of these things, we can simplify our functional equations by a lot and potentially make it so that like some very common technique like plugging everything in would just work on the problem. But what are injectivity, surjectivity, and bijectivity? Well, injectivity is when if f of x equals to f of y, then x equals to y. In other words, consider the graph of f of x. If you can draw a horizontal line which intersects the graph at more than one point, that function is not injective. But if every horizontal line intersects the graph of f of x at most once, then the function f is injective. One of the cool properties of injectivity is that it can simplify functional equations massively. Like, for example, if you are able to prove that the function is injective, then you can simplify if both sides are taken if you take f of x of both sides, then you can just remove the f without changing um, the validity of the equation. And if you solve the new equation that is much, much simpler, you can just know that it's the solution to the old equation. Surjectivity is a bit more complicated, but essentially what it says is that for every c within the range of f, so like for every c within the range, so like in the previous examples, the range was the reals. So let's say the range is the reals. So for every real number c, there exists an x such that f of x equals to c. In other words, if you draw a horizontal line across your graph of f, no matter what, that line should intersect f at least once. And this is very helpful when if you have something within f, like if you have an expression of f within f. So you can just make x, like for example, if you make f of x equals to the like c, you can always have a certain value of x such that it is equal to c, so you can make a lot of simplifications that way. And bijectivity is if f is both injective and surjective. So for every line, there's exactly one, for every horizontal line, there's exactly one point where it intersects the graph. That was a lot, so let's quickly recap what we just did. So most functional equation problems can be reduced into a few steps. So the first thing is you want to find convenient values to find very important information. So for example, you want to find what f of 0 is. You want to find what f of 1 is. Or you want to find whether something is injective, surjective, or bijective. And we can use this information to do a lot of things, but we can prove bijectivity, surjectivity, or injectivity, or other information like whether a function is odd or a function is even. And function is odd just means that f of x, so I can write it down. So odd means f of x equals to negative f of negative x. And even is just f of x equals f of negative x. These are also very useful in a lot of problems, as you'll see later, but generally you want to prove one of those big terms that you can use to your advantage later on when you want to find the answer. And after you do that, you can just plug in more things into the simpler functional equation and get an even simpler functional equation, or just find the answer. And once you find the answer, always make sure at the end to plug it back in and check if it works. Because if you don't do that, you're basically losing a free point. And so how the scoring works is there's 7 points per problem. But if you miss that last step of plugging it back in to show that it works, then you only get 6 points and you don't get this full 7 points. And so it's very, very important that you plug your function back in to check that it works. Now we'll jump into some um, contest problems that have appeared before. So this problem appeared on 2016 USMO. It looks like a problem 4 and it looks so hard, but really it's like the same difficulty as a problem 1, because the difficulty on day 1 is the same as the difficulty on day 2. So problem 1 and problem 4 are analogous in difficulty. So it's one of the easier Olympiad geometry Olympiad problems in general. Yeah, I'll give you 5 minutes to think about this problem and how you might go about solving it. If you have any ideas about the problem, like please speak up, or like at least like send a message so that, I know that you have an idea and you're not just like stuck on the problem and not knowing anything. Um, Wait another minute and then I'll go through the solution. Um, okay. I'll just go over the solution because no one sent me anything. So essentially, there are many ways to try to solve this problem, and especially with the hint, you can probably tell how we are going to try to prove that this function is even. So if you look at the equation, it looks symmetric except for one problem. It's that the function that it's multiplied by, so this part and this part is not symmetric, and it's different by sign. So at the end, it should be pretty intuitive that it is even. It is an even function. So now let's go about trying to prove that. Um, One way we can prove that is by going into this. So what this is doing is, first, we can easily see that f of 0 equals 0. And then we plug in y equals 3x. But why do we want to plug in y equals 3x? Well, the reason is because if we go back a slide, the reason is because we plug in y equals 3x, that cancels out this second term. And if it cancels out the second term, that means that we only have to work with 2 terms instead of 3, and that is much easier to work with and easier to get a result from. So we plug in y equals 3x, and we find that it is some very complicated mess, and, we don't like that. But if we similarly plug in 3y equals x, for the same reason, we want to cancel out the first term this time instead of the second term, we get a very, very similar expression. And when we compare these two expressions, we can easily see that the only difference between them is this term that I'm circling right now. So that means that f of negative 8x equals to f of 4x squared. So this is f of 4x squared over f of x plus 3x squared. And that proves that f of 8x is equal to this value by dividing through, and f of negative 8x is also equal to this value by dividing through. So that means that f of 8x equals to negative f of negative 8x. And that similarly means that f of x equals to f of negative x, which proves our initial suspicion that the function was even. Now we want to take advantage of the fact that the function is even to help us get solve the problem. So the way we can do that is we plug in y equals negative x. And the way this helps is because, first of all, it cancels out the it cancels out the term on the right. And because our function is even, it makes these two terms combine together. So it makes the first term and the second term combine together because we know that our function is even. And so when we plug this in, we get that f of x is either x squared or f of x equals to 0. And when we plug both functions back in, we see that both of them work. And so we have the answer that it's either 0 or x squared. Are there any questions? I'll pause for like 2 minutes for questions, or like 1 minute for questions, and then I'll move on to the next question. Okay, if there are no questions, we can move on to the next slide. Yeah. This problem appeared on this year's USA JMO, and it was problem number 1. So, yeah. Find all functions f. Notice that this time it is from natural numbers to natural numbers, not from reals to reals. So that might change. And natural numbers is basically positive integers. So 1, 2, 3, dot, dot, dot to infinity. So those are the natural numbers. So find all functions f from natural numbers to natural numbers such that for all positive integers a and b, we have that f of a squared plus b squared equals to f of a b times f of b, and f of a squared equals f of a squared. Yeah, and there are 2 hints here. So the first hint is that f of 1 clearly works, but is it the only solution? And the second hint is that the general form for Pythagorean triple. So if you've ever learned the generating function for Pythagorean triples, it's here. So a squared plus b squared squared equals to 2ab squared plus a squared minus b squared squared. And we want to figure out how to use that. I'll give you 3 minutes to think about this, and then I'll show the solution. Are there still no ideas? Like there are no ideas for anything? Hmm. Okay, I guess if there are no ideas, again, I'll just go over the solution again. So, the Pythagorean triple generating function is going to be very, very useful in this problem. And the way you think of using something like this is that you realize that the problem deals with a lot of squares, a lot of squares. And especially the term a squared plus b squared should definitely remind you of Pythagorean triples. So if we have a Pythagorean triple with a squared plus b squared or something like that, we could potentially be able to find that 2 different ways. And if we think that f of x equals 1, and one of the sides we already know is 1, then the other side must be 1. Both of the terms, or however many of the terms, all must be 1. And from that, we can easily figure out very big observations. So basically, the solution goes around first. If we plug in a equals 1, f of 1 equals 1, then we try to write this number. So f of a squared plus b squared all squared in multiple different ways. So simply from the first equation squared, we just get that it is equal to f of a squared times f of b squared. But if we also use the second equation first and the Pythagorean, if we use the Pythagorean triples formula, then we can use the second equation to make it f of that number squared. And then using the Pythagorean triple generation, we can split that into 2ab squared plus a squared minus b squared squared. And then we can split that further. So what that looks like is here. So you have this equals to a squared plus b squared squared, and then a squared minus b squared squared plus 2ab squared equals to f of a squared minus b squared and f of 2ab. And so now what we realize is we can just use induction. So we know that a equals 1. When f of 1, when x equals 1, f of x equals to 1. So that's the base case done. Then the next case is if all the numbers from 1 to n are even or are 1, then we split it into two cases. So if n plus 1 is even, then we can plug in a equals n plus 1 over 2 and b equals 1. And when we plug that in, we get that the left-hand side, or f of a squared times f of b squared, is clearly 1, since both of those numbers are less than n. And we also get that a squared minus b, or we don't care about a squared minus b squared, even though we know it's 1, but what we do care about is 2ab, and 2ab equals to n plus 1, and since f of 2ab equals 1, f of n plus 1 is also equal to 1. Otherwise, we can use this a equals n plus 2 over 2 and b equals n over 2, and similarly, both of these are less than n, so the left-hand side is 1, and the right-hand side is 1 also. And that means that f of a squared minus b squared equals to 1. And if we use a equals n plus 2 over 2 and b equals n over 2, then we get that n plus 1, f of n plus 1 equals to 1. So in all cases, f of n plus 1 is equal to 1. And from induction, that means that all natural numbers from 1 all the way to infinity have f of x equals to 1. Thus, f of x equals to 1. And when you check f of x equals to 1, you can clearly go back and see that 1 equals to 1 times 1, and 1 equals to 1 squared. So that works. Yeah, and that's the end of the lecture. Thank you for listening. And yeah. Thank you so much.